In this video, I want to take a look at hyperboloids. Now, these are like ellipsoids or spheres where your equation is going to have all of the squareds in it, x squared, y squared, and z squared. The difference between these hyperboloids and what we saw with ellipsoids is that some of the terms here, the quadratic terms, have negative coefficients in front of them. So in this case, I've got a 1 in front of the x squared, a 1 in front of the y squared, and a negative 1 in front of the z squared. Now I want to take a look at what the graph of this looks like. And I want to do it by looking at traces. Now I could have done this with ellipsoids as well, but I didn't, so I'm introducing the notion here. I want to look at traces. And in particular, the three main traces we look at are what happens in the coordinate planes. So for instance, in the xy plane, there is, so xy plane is the plane where z equals 0. So if I plug z equals 0 into this thing, I get the equation x squared plus y squared minus 0 equals 1. Well, I know what that is. That's a circle, right? So let me draw my 3D coordinate system here. Here's the x-axis, the y-axis, and the z-axis. So in the xy plane, this looks like the unit circle, right? Radius 1, so go 1 back and forth here, back and forth there, and so I've got this circle here in the xy plane. In the, let's say, the xz plane, well, the xz plane is where y equals 0. So if y equals 0, I'm plugging in a 0 for y there. I've got x squared minus z squared equals 1. Well, this now is an hyperbola. And so in the xz plane, I have a hyperbola where, let's see, I know hyperbolas look either like this or like that. And I have to decide which one I have. So since I'm in the xz plane, I've got an x-axis and a z-axis. And so does it hit the x-axis or does it hit the z-axis? Well, if it hits the x-axis, that's when z is equal to 0. And that would work all right. If I had x squared equals 1, then x would be plus or minus 1. On the other hand, it doesn't hit the z-axis because if x was equal to 0, then I'd have negative z squared equals 1, and that would not be good. That would mean I'd have to have some imaginary z values. Although that might be pretty fun, but we're not going to deal with that here. So this hits the x-axis, so this is the one it does. It hits the x-axis but not the z-axis. So it hits here, and then it opens like a hyperbola. This is in the background there, right? So it opens up backwards. Likewise, if I look at the, what's left, the YZ plane, the YZ plane is when x is equal to 0. So plug in x equals 0 in there, and I'm looking at y squared minus z squared equals 1. This is very much like the other one, except now it's in the YZ plane rather than the XZ plane. So it's going to hit the y-axis here and here, and it's going to be a hyperbola opening this way. Now, can you really see what's going on there? One of the things I like to do, I think I've got an idea of what's going on, but I like to look at some other slices. In particular, I think slices with different values of z would be good, because if I take this equation here and move the z over to the other side, x squared plus y squared equals 1 plus z squared. Right? No matter what value of z I plug in here, positive or negative, 1 plus z squared will be a positive number, and this will then be a circle with radius, so set it at 0, 0, with radius the square root of 1 plus z squared. Okay? So for instance, if I plug in z equals 1, so I'm looking up here at z equals 1, I've got x squared plus y squared equals 1 plus 1 squared, which would be 2. So in the plane z equals 1, this looks like a circle of radius square root of 2. So there's this circle here of radius 2. Likewise, if I plugged in -1, it would look exactly the same because the -1 squared would still be 1. And so down here at -1, you also have this circle of radius square root of 2. Right? Plug in a bigger value of z. Plug in 2. Z equals 2. You've got x squared plus y squared equals 1 plus 4, which is 5. So you have a circle of radius 5 up here. And at this point, I start to get a good idea of what this looks like. And I have had many students over the years, and then I'll start to have people saying, oh, let's shade this in, make it darker on this side over here, and light on this side, light on the darker and darker and darker and darker. Then they really make it look like a 3D thing. I don't generally do that. I get a good idea that I know what this looks like. It's got circular cross sections perpendicular to the z-axis, and then it has elliptical cross sections. Not elliptical. That would be hyperbolic cross sections when I take a plane that contains the z-axis, right? So if I take a plane going this way, the intersection is an hyperbola. Okay. You may have seen these things before. They look like cooling towers for nuclear power plants. Here's a better picture of one. This is precisely the same one we were looking at, x squared plus y squared minus z squared equals 1. And you see the hyperbolas going that way, and you see the circular cross sections when you're looking straight down the z-axis here. Okay, so this is what's called a hyperboloid of one sheet, right? Or an hyperboloid. Do you say a hyperboloid or an hyperboloid? Is the H silent? The H used to be silent, but hyperbola is a word that came down to us mainly through written language, not spoken language, so people didn't realize how it was initially pronounced, and so now people say the H. If you look in some old math books, they will say an hyperbola, whatever. Interesting thing about the hyperbola is the hyperboloid of one sheet here, it is what's called a ruled surface, that at every point on the surface there contains a line, and in fact this is doubly ruled, there's two lines, that are completely contained, a perfectly straight line that are completely contained on that surface. Now this is hard to see in this picture, but my claim is that when I look like this, that there's spots here and here that as we're looking at, well this one's the best one at the moment, where it pinches down to almost nothing. Because what we're doing is we're looking straight down a line, and the whole surface is lining up with that line, and that line is completely contained. There are two lines at every point completely contained on the surface. It's a doubly ruled surface. Now, notice that this has one minus sign here, and it's called a hyperboloid of one sheet. Well, it's not because there's one minus sign that it's hyperboloid of one sheet. It's one sheet because it's just one connected surface here. Right? But notice that the minus sign is in front of the z squared here, and the axis of rotation here, the axis that doesn't get hit by this thing, this axis through the center here is the z-axis, and there's a minus sign there on the z. If you had it set up with a minus sign on the x squared and a plus sign on the z squared, then this thing would be centered around the x-axis. Likewise, if the minus sign was with y, it would be centered around the y-axis. Okay. Now, as you change the values of, so this I don't know if I said this yet. We can set these up very much like we did with the ellipsoids, where you want to do x squared over a squared plus y squared over b squared plus, or minus z squared over c squared equals 1, because the a, b, and c determine how wide this thing opens up. So for instance, if I take this a and turn it into a 2, then it's hitting the x-axis at plus or minus 2, where it's hitting the y-axis at why I ask, right? So back and forth 2 here on the x-axis, but only back and forth 1 on the y-axis. If I wanted it, be a wider opening on the y-axis, I could change b here to something else, let's say 3, right? So that would now be a y squared over 9, because it's b squared. And you can see it goes back and forth 3 there on the y-axis. Now it's hard to tell what's happening with the z because it never touches the z-axis. There's a bounding rectangle with hyperbolas. I'll switch back over here for a moment. Right? With hyperbolas, you have this bounding rectangle. So if this is x squared minus y, so let's say x squared over a squared minus y squared over b squared equals 1, I go back and forth a on the x-axis and back and forth b on the y-axis. And if that was a plus sign, you draw an ellipse inside that rectangle. With a minus sign, you draw the 2 diagonals, and those are the asymptotes of your hyperbola. I'm hoping this is a review of something you learned in pre-calc. And then the hyperbola either opens up above or down below. And in this case, it's okay for y to be 0. So you can hit the x-axis here, but it's not okay for x to be 0 because that minus sign, you can't have the negative stuff equaling 1. So anyway, the hyperbola opens, here and there. But those lines are the asymptotes for the hyperbola. Right? The hyperbola gets closer and closer to them as you go up to infinity there. So it's really hard to see the b when you're just looking at that hyperbola. Coming back to this thing right here, it does change things, however. Let me see if I can get it to where I can see the z again. So looking in this direction, if I change what I'm dividing by for the z here, so let's change that to a 2, you'll be able to see that it does stretch it vertically. Right? It stretches it vertically, but it's hard to really place precisely where the thing is. Next, I'm going to look at this picture right here. So in this picture, what I have is I have a hyperboloid of 1 sheet. You can see over the side here, this is going to be a hyperboloid of 2 sheets. That's the next video. But this one is drawn a little differently. This is drawn with the lines that are completely contained on the surface emphasized. Okay. And it animates to show a couple of things. This can be made out of string. You can essentially have a circle up on the top and a circle down on the bottom, and you can connect string from the top to the bottom, and then move over from the top, and keep the slope the same each time as you work your way around. And you have, oh, that's not what I want. Stop right at any one of these points here, like that. You have a hyperboloid of 1 sheet. And as this is spinning around, what's happening is the relationship between A and B and C are changing to get different hyperboloids, but each one of these is a hyperboloid of 1 sheet. There's a couple of interesting stopping points here. One is right there, where this hyperboloid actually shrinks down to a cone. We will talk about cones in a subsequent video. And the other interesting spot is right here. I didn't quite get it. I went past it. Here we go. Try again. I want to stop when it's right on the edge. Maybe I can get it. Maybe I can't. Now, that's pretty close. This is a cylinder, right? So we'll see how this works in the video when we talk about cones. It's essentially a degenerate form of a hyperboloid, turns into either a cone or a cylinder, and we'll see how that works again in another video. So I think that's enough for these things. You work with them, the equations very much the same way as you work with ellipsoids. If you want to try to find the center, you're probably going to have to complete some squares. And then it's the same process, except that you've got a minus sign floating around in front of one of the quadratic terms. Okay. Anyway, hyperboloids, 1 sheet.